Inside the thunderous roar of a massive rocket, there's a hidden force, a tiny rhythmic shake that can actually grow powerful enough to tear the entire thing apart. It's called vortex shedding, and for a long time, it was one of the biggest mysteries in engineering. So imagine this. You've got the best engineers in the world working on these massive, solid rocket boosters for the space shuttle, for Ariane 5, and they run all the numbers. Every single one of their trusted models came back with the exact same answer. These motors should be rock solid, perfectly stable. And yet, when they actually test-fired these things, something was off. Something was causing these colossal rockets to vibrate in a way that just made no sense. The models said it was impossible, but the real-world data was telling a completely different story. And this right here, this is the evidence they saw. This plot is basically a series of snapshots of the pressure inside the motor. And each one of those repeating peaks, that's a steady, low-level vibration. Now, it wasn't violent, but it was incredibly persistent. And every engineer knew that if that specific frequency matched the rocket's own natural vibration, the whole thing could just shake itself to pieces. Yeah, this wasn't just some interesting science problem. The fact that these little vibrations could team up with the launcher's structure was, as the source material puts it, a serious point of concern. Figuring out this unexplained shake shot right to the top of the priority list. And this was the aha moment, the big clue. The pitch of the vibration, its frequency, wasn't constant. It actually dropped as the solid fuel burned away. Now, what does that tell you? It means the vibration wasn't connected to the rocket's fixed physical structure. No, it had to be connected to the gas moving inside the motor. Okay, so if it's not the rocket itself, what in the world could it be? Investigators started looking really closely at the physics of that superheated high-speed gas roaring through the booster, and they had a prime suspect. And that culprit is a phenomenon called vortex shedding. You've actually seen this a million times. Think about a flag flapping in the wind, or that humming sound a wire makes on a really windy day. As any fluid, air, water, or in this case, rocket gas, flows past an object, it creates these little whirlpools, or vortices, that peel off in a super regular repeating pattern. And that pattern creates a vibration. But see, out in the open air, that's usually not a big deal. Inside a rocket, though, vortex shedding has a dangerous partner in crime: acoustic coupling. So when one of those vortices hits a surface, like the rocket nozzle, it creates a little pressure pulse, basically a sound wave. In a closed space like a rocket motor, that sound wave travels back upstream and can arrive at the perfect time to organize the creation of the next vortex, making it even stronger. This diagram just lays out that vicious cycle perfectly. A vortex is born, it travels downstream, it smacks into a surface, and that creates a pressure wave. That wave provides feedback that organizes and beefs up the next vortex. And boom, you've got a self-sustaining, locked-in vibration, the mysterious shake. So this was a fantastic theory, right? But to prove it, scientists needed a way to spot the unique fingerprint of this process. They had to find a way to measure it and predict it, to turn this cool idea into a tool they could actually use to build safer rockets. And that fingerprint is a simple, elegant thing called the Stroll number. It's just a dimensionless ratio that connects the frequency of the vibration to the speed of the gas flow and the size of whatever is creating the vortices. And the cool thing is, for any given shape, this number stays remarkably consistent. It's the signature they were looking for. Now, the tricky part is that a rocket motor is a pretty complex place. Vortices can get kicked off by all sorts of different things. So the scientists needed a few different versions of this fingerprint. One version looked at vortices spinning off physical things, like a ring inside the motor. Another focused on what's called the shear layer. That's the turbulent edge where fast and slow-moving gases grind against each other. And a third measured the timing of that sound wave feedback loop. They're all describing the same basic problem, just from slightly different angles. All right, now we get to the best part of any detective story: the smoking gun. To prove their theory beyond a shadow of a doubt, scientists at the French aerospace lab ONERA decided to do something pretty wild. They decided to intentionally build a rocket motor that would whistle in a perfectly predictable way. And this was basically their recipe. First, they designed the solid fuel to create a perfect shear layer, that ideal boundary for making vortices. Then, they calculated the exact frequency where those vortices would go haywire, and they tuned the length of the motor so its own natural acoustic ring matched that frequency perfectly. Then they just had to make sure the gas was flowing at exactly the right speed to hit that trigger point. It was precision engineering designed to create a controlled failure. And guess what? It worked. Oh, it worked perfectly. On the left here, you can see the design of their little experimental motor. And on the right, that's the money shot. Look at that incredibly sharp, clean peak in the pressure data. That is the whistle they predicted, a powerful, pure-tone vibration created completely on command. This was the irrefutable proof they needed. So, with the mystery solved, the next challenge was figuring out how to tame this force. This incredible research didn't just explain the problem, it gave engineers the exact tools they needed to design it right out of future rockets. And today, we have a tool that those pioneers back in the 70s and 80s could only have dreamed of: massive supercomputers that can run full-blown simulations of the entire motor. What these simulations do is make the invisible visible. Engineers can now literally sit and watch on a screen as these vortices are born, as they travel down the motor, and see how they interact with the sound waves. They can test a dozen designs virtually and stamp out these instabilities long before a single piece of hardware is ever built. And you know, this work is more important today than it has ever been. We're building rockets now that are more powerful than anything that's come before for these incredibly ambitious missions to the moon and Mars, and reliability is everything. The fundamental physics figured out in this research is now the absolute bedrock of the analysis that keeps these modern rockets safe. It really leaves you with a critical question. We solved the mystery of the rocket's secret shake? Sure. But as we build these colossal new engines that are going to take us to Mars and beyond, what other impossible vibrations might be hiding in the fire, just waiting to be discovered?